Hey, it's the last day of September. Tomorrow's October. Whee! So these are, it's interesting that they have this name. Another name for it is like just a horizontal shift, like a horizontal translation. Phase shift sounds like all high tech and fancy and stuff though. So what we've done so far with our graphs is we have used amplitude to stretch and compress them vertically to make them taller and shorter. We've used midline adjustments to physically pick up the whole graph and move it up or down. And then last week, late, we learned how to do period adjustments where we make the graph repeat itself either more or less frequently. So the final piece of the puzzle is the phase shift, which again is just like what we would call like a horizontal translation. So it takes an entire curve and it shifts it to the left or it shifts it to the right. Now, in these first couple examples, that's all you're going to see is just a phase shift and nothing else. So I thought about it and I thought, let's start with one where all we do is move. So these are our warm-ups. So that's the last place that you could see a number in a trig function. It's like we've seen it out in front, amplitude, you've seen it attached to the x for period, and you've seen it after the parentheses for vertical adjustment. So if you have a plus or a minus something inside with your argument, x or theta, whatever, then that actually moves the graph right or left. So the thing you have to remember about phase shifts is that they're backwards, and some of them can be done very easily mentally. Throughout the lesson, you'll see that not all of them can. But in a case like this, what this phase shift implies is that the whole graph is going to get up and move to the right pi over 4 units. And that's going to take everything, the entire sine curve, and move its starting and stopping positions exactly pi over 4 spaces to the right. And it's to the right because, as you've often seen in math, centering or making something equal 0 is critical. So like if I put pi over 4 right here in place of x, what's pi over 4 minus pi over 4? That's the goal, is always to center, to create that centering out, that canceling out. And so that's why phase shifts are going to be backwards of what your brain initially tells you. You see a minus, you phase shift right. You see a plus, you phase shift left. Dead opposite of what you think it ought to be. So get used to that. So already this can get a little nasty if you think about, okay, so normally a graph, a sine curve normally would start at 0. And then it's 4 other marker points. The ones that we have become familiar with are pi over 2, pi, 3 pi over 2, and 2 pi. So for any sine or cosine curve, like a week and a half ago, before it started getting a little bit more confusing, those were our 5 default mark points every time, right? Like you would go start, top of the circle, left, bottom, home, every time, just those 5 predictably. But what happens if we phase shift all of those pi over 4 units to the right? Well, now the graph has a different starting point, and every one of those 5 points then has to change. So if I phase shift to the right pi over 4 units, what does 0 become? It does. And so now the graph actually, quote unquote, starts at pi over 4. This cycle of it, this period of it starts at pi over 4. Where does pi over 2 phase shift into? 3 pi over 4. What does pi phase shift into? Correct. What does 3 pi over 2 phase shift into? 7 pi over 4. Good. And then what does 2 pi shift into? 9 pi over 4. Good. And that is not pleasant for anyone in the room who might be struggling with the basics as to what is happening. There's a lot of basic math going on there that in a perfect world, we all know, right? In order to add pi over 4 to all of those locations, I had to make a denominator, which is, I'm sure, exactly what you guys did. So like for pi over 2, those of you that were saying those answers, I'm sure that in your brain, you thought of pi over 2 as 2 pi over 4, which enabled you then to add the pi over 4 to make the shift. And I'm guessing that you thought of pi as 4 pi over 4, and 3 pi over 2 was 6 pi over 4, and then 2 pi was, of course, 8 pi over 4, right? So having that basic understanding of grade school math actually applies itself here in a very non-grade schooly class. And that is like, if I have the same denominators, then I can add and subtract things. So these would be the 5 locations where we would graph. And so if we made a graph of y equals sine of x minus pi over 4, it's going to look the same to us. The structure of it's going to be identical. We're going to make our x-axis and our y-axis. And this time we're going to have different parts that we mark down. So when we make our marks, we're not going to be so interested in 0. We're going to start actually at pi over 4. And then kind of how you want to do this is up to you. Depends on like which kind of art style suits you better. But some people might start at pi over 4 and go all the way over and mark 9 pi over 4. And then you can subdivide and mark the other spaces or the other tick marks based on just proportionality. Like what's the halfway tick going to be? Good. And then of course the low halfway is going to be 3 pi over 4. And then the high mid is going to be 7 pi over 4. Okay. Same thinking is going to apply. I didn't put any midline adjustment. I didn't put any period adjustment, no amplitude adjustment on this one. So this would be a default graph, but the difference this time is that let's go ahead and mark our y-axis. Let's stick a 1 up here and a -1. Because as you know, a default sine or a default cosine is going to waffle between 1 and -1, right? And so where will this sine curve start? Yeah, I mean, like relative to the highway, the high, middle, and low, where does sine start? On the midline, right? The midline. That was a tough word to get out of you there, so thank you. So this graph actually starts on the midline, which look at how odd that is. It starts right there for the first time ever. It doesn't start at the origin. We don't want it at the origin because the origin, it got phase shifted off the origin. The whole graph got moved to the right pi over 4 spaces. And now the pattern will, of course, continue. That's why I'm teaching it to you this way, so that when we get the meat and potatoes part of it down, that's maybe not the right expression, but like when we get the difficult mathy part done, then the patterns just are what they are. Like I trust by now you know how sines behave and negative cosines, like you get the flow of the points. And so which way is this graph going to go? Sine curve. It's going to start up in this case because there's no negative in front to make it go down. So it's going to follow the typical sine pattern of go up, go back to the midline, go down, go back to the midline, like such. And when we make a sketch like this, we want to be aware, again, these are the kind of things that people do that just, I don't know, it doesn't make me mad. It's just kind of breaks my heart. Like that's a really bad tail to draw, right? Because then you're completely ignoring the fact that this curve has to work its way down and head towards down here like this, maybe something like that. And so then it's going to come up. And I don't have my highways drawn, but just for this example, I figured what the heck. So like such, and then again, it's going to curve and do something like that. All right, to someone walking in, it's not a big deal, but to us, we understand that that was a big deal. We did not start this on the y-axis. It didn't start at the vertical line. It got phase shifted off. So all 5 points were off kilter. Okay. Let's do one more simple one, and then I'm going to make them progressively more difficult as we go. So that one should have been pretty new, but not that bad. Let's do y equals the negative of the cosine of x plus 2 pi over 3. No amplitude adjustment, no midline adjustment. So this, like his predecessor, is going to waffle back and forth around just the default x-axis. What's the phase shift going to be? Good job. It's going to actually be left 2 pi over 3. Nice and simple. So sometimes it helps to think about the OG numbers, like what were they before we went and moved around with them. So, and you'll find I have other strategies I'll give you over the next half hour, but like you'll come up with your own little power plays that work better for you. At this point in the lesson, though, I'm inclined to write down all the defaults. So we have 0, pi over 2, pi, 3 pi over 2, 2 pi. Those are our 5 guys, our standbys. Now, if we shift left 2 pi over 3, what does 0 become? What's left of 0 by 2 pi over 3? What if I told you on the number line to go left of 0 by 5? What number is, it's a negative. Very good. So it's negative 2 pi over 3. Very good.
I'll think about like
This way, like.
going
going-
from 2 pi over.
Yeah.
Interesting. Nope, we're just literally looking at xness. So instead of sitting at the number 0, if I say go left, you just essentially do 0 minus 2 pi over 3, and there you are at negative 2 pi over 3. Got it? What is pi over 2 going to shift into? And you better be thinking about a common denominator. Right now, your brain ought to be calling this 3 pi over 6, and your brain should be calling the phase shift 4 pi over 6 because denominators have to be the same. So if I start at 3 pi over shift and phase shift left 4 pi over 6, what am I? Try that again. I'm at 3 pi over 6, and I'm going to shift left 4 pi over 6. I am at negative 1 pi over 6. Okay. And they say this isn't the only way to do this. I'll present other methods as we go through, but I felt like at this point it seemed right. If I take a pi, whole pi, and I phase shift it to the left 2 pi's over 3, what is that going to be? Nice job. If I take 3 pi over 2 and I phase shift it left, and again, I'm sorry for the 4th grade math lesson here, but it's not just for 4th grade. Common denominators are massively useful. 3 pi over 2 right now in your brain, you should be calling it 9 pi over 6 so that it can be compatible with the shift that we have to do of 4 pi over 6. So if we start at 9 pi over 6 by default and go left 4 pi over 6, where are we? We're at 5 pi over 6. And then finally, we have 2 pi, which we should right now be thinking of as 6 pi over 3. I'm going to be, that denominator is like a chameleon. It's going to change to whatever situation it's faced with. If you have to add it with something that's got a 3 on the bottom, then you make it have a 3 on the bottom. But what's 6 pi over 3 minus 2 pi over 3? Yeah. And so our final point is 4 pi over 3. So that's the key, is getting those 5 points labeled. I don't need any more. I don't need any of the mid quadrantal angles, just as it has always been the case, is those critical 5 points. So again, we're going to make a graph, and the key is those will be our labels. So we're going to have our x-axis and our y-axis. And now we just want to think about proportionality. It doesn't have to be perfect, but we should be thinking and like conscientious about trying to not make it be too off scale. The x-axis we should worry about. The y-axis is, like I said, kind of up for debate. So we're going to mark our beginning point at negative 2 pi over 3. And now we're going to start counting our way up. So you want to be smart about this, and like, where do we know negative pi over 6 has to go? Yeah, but still to the left, right? So like I would say it might go here, something like this. And you'll notice I'm subdividing a little bit differently this time. And that's because I didn't want to put myself in a position where I was forced artistically to put negative pi over 6 to the right, because that just is dumb, right? So now what I'm going to do is probably just keep the flow alive. And I'm just going to kind of estimate that I bet pi over 3 is probably right about here. And I'm going to go ahead and guess that 5 pi over 6 is probably right about here. And then finally, I'm going to guess that my 4 pi over 3 is probably right about here. Okay. What are the max and min going to be for this particular graph?
Still.
For sure, still a 1 and a negative 1. That's going to change here soon, but for now, barring any alterations to the amplitude, then we know that it just waffles between 1 and -1. Now, it is a cosine curve, and it's a negative cosine curve. So where's it going to start?
Maybe what the actually. Maybe two.
It's going to start right there where the big red dot is. Okay. Everybody buy that? So building that period is huge. That's like our one thing to hold on to is that if you give me one period, then I can fit what I understand about sine, negative sine, cosine, negative cosine. You just bring it all day and I'll just plug in my points like a robot. And now as we work our way through the 5 points, we're going to follow the cosine pattern. It's going to go low, mid, high, mid, low, like such. And then when we go to make the sketch, we're going to try to be conscientious of its behavior, its curvature, such like this, maybe. So far, do you have any questions? Now, where it gets more interesting is when we try to do two things at once. So all we've done so far is just keep a standard graph that is 2 pi units long, and we've just shifted it left or right. What we're going to do now, though, is where phase shift really gets the claws come out. And when you try to move something while shrinking it or expanding it, odd things happen. Think about those two things trying to happen together. Really let your brain try to get around that and say, okay, so wait a second, you want me to move this thing so many units to the left while also shrinking it. You start to think about that, you're like, wow, how does that impact the left and the right sides? I'll show you. And it's very difficult to do. These ones, I believe, if you're paying attention, we can probably just fudge our way through like we just did. But as they get tougher, like now, I'm going to show you a better way. So for our next one, and there will not be an assignment today, by the way. So I've made that choice. I knew this lecture would take all hour, so don't stress. I'll give you a break here in a few minutes. Let's just, again, let's keep it the same. No amplitude adjustment. Let's just do a basic sine curve. But the argument of the function is going to be 4x minus 5 pi over 6. So this is really where the nastiness starts to come out, because now we've got two things affecting the graph. We've got a phase shift. And it's very easy for you to say that the phase shift is right 5 pi over 6, but it's actually not. And the reason for that is because as the phase shift happens and as the graph gets pushed to the right, it's also being shrunken by a factor of ×4 or divided by 4. And there's really no words I can have. I could probably find like a YouTube animation that would show what I'm trying to say, but as something shrinks and moves, the sides of it behave in very interesting ways. So in order to find the new boundaries, this is a trick a coworker of mine showed me 20 years ago. And I was like, yeah, this is how it should always be taught. We'll never teach it any way other than this again. What you want to do to find your period is you want to take the 4x minus 5 pi over 6. This is a good one. You're going to want this. And if you go on to take more advanced trigonometry classes, you can use this for tangent graphs, cotangent graphs, secant graphs, cosecant graphs. It all starts with this. You take your argument of your function and you wedge it as a compound inequality in between the default starting and ending points of one period. You could use any period. You could have gone 2 pi to 4 pi, 4 pi to 6 pi. We, of course, though, because we're not idiots, we're not masochists, we're going to choose the 0 and the 2 pi. Now, the beauty of this method is that if we solve this inequality from the inside out, the resulting numbers on the left and the right will be the boundaries of a period, which is what we want. So, are you ready? How do we get x by itself? Take a shot. Let me remind you of something from way back in the day. This is a long time ago for you guys. If I gave you x minus 4, and then I said it's like greater than -2, but less than 10, do you know how to get x by itself? You would add 4 to all three sides. Sounds weird to say, but there's a middle and a left and a right. So if I add 4, I get 2, I get x, and I get 14. You agree with that? Okay, so we're going to employ that same basic algebraic thinking to this one. Follow your instincts. How do we solve that red inequality? Let's start by adding 5 pi over 6. So I'm going to add 5 pi over 6 in the middle, and I'm going to add it on the left, and I'm going to add it on the right. My left side is now going to say 5 pi over 6. My middle is now just cut down to just 4x. And on my right, again, I'm sorry for the basic math test, but I've been telling you for years that it's kind of important, right? What is 2 pi plus 5 pi over 6? I heard something, but I don't know what it was. It's 17 pi over 6. And if you're wondering how we got that, here's a quick explanation. We made 2 pi into 12 pi over 6. And why did we do that? Because we needed it to have the same bottom as the guy that's going to come in and add to him. 12 pi's over 6 plus 5 pi's over 6 makes 17 pi's over 6. Now think about the inequality that's on the board. It's a simpler version of his predecessor. How would we get x now officially by himself? We would divide everything by 4. And I'm going to show my work on this step just so that we can all perfectly see what's going on. When we divide by 4, we've finished. The problem's over, but we just don't have the math quite done. So I need to say, x, you're now isolated. And I have you isolated in between a couple of math answers. What's 5 pi over 6 divided by 4? Please, it is. And just always remember this, and this because you're going to use this a lot. When you divide by a whole number, you really just multiply the bottom of the fraction by the whole number. So if I said to you, make that red fraction divide by 4, you actually just multiply the bottom by 4. Then you get 5 pi over 24. That's our new left side. Done. What's the right side going to be?
17.
We now have 1 period. And that's interesting because you can see the phase shift wound up not being 5 pi over 6 like the problem initially implied. It wound up being 5 pi over 6 divided by 4. So the phase shift is like this conglomerate, that's not the right word, like a coalescence or something. It's like things come together, these two forces at play. The fact that the period shrank and also got moved caused these interesting boundaries to occur. So now when we go to make a graph, we're going to need our 5 key points. And don't make this too difficult. This part I know can be a little bit stressful, but if I start at 5 pi over 24 and I end at 17 pi over 24, what's halfway in between there? How far is it from 5 to 17? What's half of 12? So that means if you come in 6 from either way, you'll find the midpoint. What's halfway then? There you go. So the midpoint is 11 pi over 24. What's halfway between 5 pi over 24 and 11 pi over 24? I'll ask the same question again. Thank you. Halfway between 5 and 11 is 8. So in the middle, we would have 8 pi over 24. But what's wrong with 8 pi over 24? It needs to be reduced. So it is going to reduce to pi over 3. And then finally, what's halfway between 11 pi over 24 and 17? Brooklyn, are you okay? Okay. And so what is it? 14 pi over 24, which again, if we reduce it down is 7 pi over 12. The problem is at this point over. I mean, I hope you understand what I mean when I say that. The math is done. Now all we have to do is set the graph up. So we're going to make our x-axis, we're going to make our y-axis. And again, since we still don't have any midline adjustment, then we can just focus on this. Don't worry too much about perfect scaling. This is nice because all the action's happening on one side. That last problem, when it crisscrosses over the y-axis, that's kind of poopy because then you got to be a little more mindful of your spacing. But here, I could just kind of, it's a little bit of a freestyle. I can just put 5 pi over 24 right here. And that's that. And then I'm going to go all the way out here and put 17 pi over 24. And now I'm going to mark all the math we just did is going to come in handy now so that I can mark my graph. So I'm going to go to the center and put 11 pi over 24. I'm going to go to the center of the bottom and put pi over 3. And then I'm going to go to the center of the top and put 7 pi over 12. And now the problem is effectively done, right? What kind of curve is this?
The sine curve, so
And is it a negative sign or a regular sign? Did it have a negative on it? I don't remember because it's up above. But so if it's just a regular sign, then we know how it's going to behave. It's going to start at the middle and just go mid, high, mid, low, mid, just like a sign always does.
We usually start at 5, 5.
You do. So like basically, and I should draw this right now, and I don't know if this will help any of you, but this box right here, this would help me if I were you, so maybe not. This box right here is where your period will take place. Got that? So this graph is going to occur within that box. I mean, the period of it that we're drawing is going to occur within that box. So it will start on the midline, and then it's going to go high. It's going to come back to mid. It's going to go low, come back to mid, done. As you can see, the real meat and potatoes part of today's lesson is getting the period set up, the first point and then the 4 other points. Good. You guys want to try one without me?
Sure.
Okay. And we haven't gotten to the full shebang yet, but I think if we can get through these first few, I hope so. Yeah. But I'm not too worried about it. Like if we don't, I'm not going to rush through it just to get it done because the clock's telling me there's no way we're going to finish everything I want to get done. So I'm not worried. I want you to try this one. And honestly, I don't need you to make a graph so much, but I would like you to get the, like, remember up here, not that, up here, how I like set it up with my green numbers. I'd like you to at least get that far without me. And then the dots we can talk about if you're having a hard time with that. But these 5 numbers are the key. So again, no amplitude adjustment on this one, no vertical adjustment on this one. Right now, all I'm after is can you do the phase shifts? So we're going to do cosine of x over 3 plus 3 pi over 4. And see what you come up with. So I'm going to pause the recording, and then when you guys, how long do you need? Just a few minutes, maybe? Oh, we'll see. And then when you're done, I'll unpause. Your first step should look like this. So remember, the setup is critical. You place the argument of your sine function in between a known set of boundaries. 0 and 2 pi is most common and simple. And then you want to do the algebra, chipping away at it, getting x by itself. So we start by subtracting 3 pi over 4. And those red numbers are what you should be at right now. If you're struggling with these numbers, you're probably not struggling with the one with the purple arrow pointing to it. But if you're struggling with the one with the yellow arrow, then you and I just need to sit down and talk about how to do it. Because you may not be comfortable asking I don't know, or maybe you just all get it, but the denominators are going to be what's getting you if you're having a hard time. So once we make it this far, the next step is to multiply by 3. And you know that with equations that when you have x over 3, you multiply to get x by itself. So I know I said you do this by yourself, but I'm guessing you're probably already done. So when I multiply the whole thing by 3, what does my left number become?
-9.
No, just -9 pi over 4. Remember that the 3 is like a 3 over 1. So it multiplies, of course, to the top, but then it's spent. So there we set a boundary. So we have -9 pi over 4 is less than or equal to x is less than or equal to. And then on the right-hand side, if we multiply also by 3, what do we get?
15.
Nice, we get 15 pi over 4. So at this point, if I said to you, you need to make a list of the 5 numbers, if you were really lost, you wouldn't even know that we already have 2, right? Well, that we have the first and the last. Now we just need to find the second, the third, and the fourth. So let's list those out. Now we got to do math. There's no getting around the math we have to now do. So we have -9 pi over 4. And then all the way over here, we have positive 15 pi over 4. And the math doesn't have to be hard if you can just relax and think about it. Go back to something I said a while ago. Whenever someone asks you to find the middle of 2 things, you should always want to know how far apart they are. Like if someone said, Mr. Ahern and Brady are going to walk and meet in the middle, I'd want to know how far apart we are. And then my instruction to him would be, let's each split it and walk half of it, right? That's how it works. So how far is it from -9? And we can say this because the denominators are the same. How far is it from -9 to 15? 24. And what's half of 24 if we split the difference? 12. So you can either come up 12 from -9 or come down 12 from 15. That will accomplish the same objective of meeting at the halfway point. And what is the halfway point? It's 3 pi over 4. And again, that you can either see as I came up 12 from the little guy, or I went down 12 from the big guy. And then the math works again. Like these are problems right now where the math is being pretty nice to us because all the tops are evenly spaced. And so how far, follow the red circles, how far is it from -9 to 3? 12. What's half of 12? 6. And so you can either come up 6 or down 6. No one cares. Either way, what will that put us at? -3 pi over 4. So we now have bottom, quarter way, halfway, and now we just need 3/4 way. And the math again isn't that bad. From 3 to 15 is a difference of 12. Half of 12 is 6. If you come up 6, you're at 9 pi over 4. Got it? How are you feeling right now? Is it not bad? Not bad at all? Good. Okay, let's do one more, and then I have 4 more examples, and we're not getting to them. We're gonna do one, and we'll leave on this, and then we're gonna just not think about this class for 23 hours. I mean, I will. You don't have to. And then tomorrow we'll resume the notes. I should have known this would probably be a little longer than 40 minutes. So one more. Good. All right. Y equals -2 times the sine of 3x over 4 plus pi over 6 plus 5. So this is the top of the mountain. When we talked like 2 or 3 weeks ago, when we first started graphing trig curves, I made reference to this, and this is the thing to which I made reference. Like this is all of the transformations. There's a flip, there's an amplitude stretch, there's a period change, there's a horizontal shift, and there's a midline adjustment. So this is just everything. So let's start by finding a period. That's a really good first move. I'm kind of feeling like the way we're doing this is clicking. Either that or I'm just putting you to sleep. So let's find a period. I'm going to do it up on the board. You're going to maybe try it without looking. So I'm going to take this. And what am I going to wedge it in between again? Nice. So these red numbers, as they change, why did I write 24? As the red numbers change, then our boundaries are changing. An adept mathematician, a talented, good mathematician, a confident mathematician would do this next step at once. I'm not going to. I'm going to do it in 2 steps. So I'm assuming you all got to this point, that you subtracted 1 pi over 6 and arrived at this. What we should do now is we should take this in baby steps. I never mean offense by that expression, but if we just multiply by 4, take your time. Because that'll accomplish one objective, but not everything we need. But if we multiply by 4, what do we get on the left?
-4.
Good. And, would we reduce that? Yes, but for the sake of just getting through this, you just leave it alone for right now. It's not going to hurt anybody. Now, because we multiplied by 4, the center is now just knocked down to a normal 3x. If we multiply on the right side by 4, what do we get?
44 pi over 6.
Nice. But remember, right. And so if you'd like, while we're here, if you're comfortable, then let's reduce now. So our negative 4 pi over 6 is actually negative 2 pi over 3. And then our 44 pi over 6 on the right is actually 22 pi over 3. What's the last thing we have to do? Yes, and remember the words from a half an hour ago, when you want to divide a fraction by 3, what do you actually do? You just multiply the bottom by 3. Very good. So to get x officially by himself, we divide by 3, and then the left side is now done. It becomes negative 2 pi over 3 times 3, which is 9. And then in the center, we have our x, and then on the right, we have what? 22 pi over 9. And I do have to wrap it up there just because I think the bell's going to ring in 45 seconds. So we'll pick it up right here tomorrow. Yep.